Have you ever just watched a thunderstorm and been, completely blown away by the raw power flashing across the sky? It's got to be one of nature's most spectacular shows, and also one of the most misunderstood. So let's get into it and uncover the truly shocking science behind a single bolt of lightning.
Okay, let's just start with a number that is, well, it's almost impossible to wrap your head around. A single bolt of lightning, it heats the air around it to 30,000 degrees Celsius. To put that in perspective for you, that is 5 times hotter than the surface of the sun. Just an incredible, mind-boggling amount of energy.
So, the big question is, how on earth does our atmosphere take a simple, puffy cloud and turn it into this supercharged force of nature? How does it generate that kind of insane power?
Well, to answer that, we've got to go back to the beginning. We need to understand the conditions that are required to even get a storm started. You see, it all begins with a very specific atmospheric recipe.
Yeah, think of it like baking a cake, right? You need the right ingredients. For a thunderstorm, you need a nice warm atmosphere down near the ground, you need pretty low wind, and you need a lot of water vapor in the air. This is why you see so much lightning activity in certain tropical regions during those periods between monsoon seasons. They just have the perfect conditions.
And the main character in this whole drama? It's the cumulonimbus cloud. Now, these are not your average, fluffy, happy little white clouds. No way. These things are absolute giants, massive towers of moisture that can stretch up to 15,000 meters high. That's higher than most commercial airplanes fly. Just huge.
Okay, so we've got this colossal cloud. How does it go from being a big puff of water vapor to a giant electrical generator in the sky? Well, the answer lies deep inside.
Picture this. Inside that cloud, you've got these powerful updrafts just whipping tiny water droplets and ice crystals all over the place. As they're zooming past each other, they rub together, creating friction. You know, it's exactly like when you rub a balloon on your hair and it gets all staticky. This friction starts knocking electrons loose, and that's what separates the electrical charges.
And what you end up with is, well, the cloud basically turns itself into a massive battery floating in the sky. It gets a positive charge up at the top and a negative one down at the bottom. See, the lighter, positively charged particles get swept upwards by those drafts, while the heavier, negatively charged ones sink down.
So now we've got this giant charged-up battery hanging out in the sky. And like any battery that's overcharged, it's only a matter of time before all that pent-up energy has to go somewhere.
And that energy can be released in a few different ways. Sometimes it jumps from one cloud to another, or even from a cloud just out into the air. But the one we really care about, the one that's the most dangerous for us down here, is cloud-to-ground lightning. So here's how that works. You see, that powerful negative charge at the bottom of the cloud actually pushes away negative charges on the ground right below it. This creates a kind of shadow of positive charge on the Earth's surface. Now, air is normally a great insulator, but when that electrical imbalance gets to be too much, the air just can't hold it back anymore. And bam! A massive electrical current violently jumps that gap. That's the lightning bolt we see.
All right, we've all done this, right? You see that brilliant flash of lightning, and then you wait for it. 1, 2, 3, and boom, the thunder rolls in. So what's up with that delay? Why don't they happen at the same time?
Well, it all comes down to a race, and it's not even a fair one. The flash and the boom are created at the exact same moment. But light travels at an absolutely insane 300 million meters per second. It gets to our eyes almost instantly. Sound, on the other hand, well, it kind of plods along at just 330 meters per second. So yeah, light wins the race to your eyes every single time.
But hey, we can actually use that delay to our advantage with this really handy trick called the kilometer rule. It's simple. When you see the flash, just start counting the seconds until you hear the thunder. Then, take that number and divide it by 3. The answer you get is a surprisingly accurate estimate of how many kilometers away that lightning strike was. So, for example, if you count 12 seconds, divide by 3, the storm is about 4 kilometers away. Pretty cool, right?
Okay, so we've covered the science up in the sky. But the real danger, of course, is how all that energy interacts with us down here on the ground. And believe me, it's not always in the ways you might expect. First up, you've got the most obvious one, a direct strike. This is where a person, usually out in an open area, literally becomes the path for the lightning current to get to the ground. It's incredibly rare, thank goodness, but it's almost always devastating.
Now, a much more common threat is something called a side flash. This is what happens when lightning hits a taller object, like a tree that you might be hiding under for shelter.
The current travels down the tree, but then it can actually jump sideways to a person standing nearby, because it's looking for an easier path to the ground. This is exactly why you're told to never stand under a tree in a thunderstorm.
Then you've got contact voltage. This is the danger you face when you're touching something that gets struck by lightning. We're talking about things like metal fences, for sure, but this can also happen inside your own home with old corded phones or even electrical appliances that are plugged into the wall.
And finally, there's one of the most surprising dangers of all. It's called step potential. When lightning hits the ground, the electrical current spreads out, kind of like ripples in a pond. If you're standing in that zone, the current can literally travel up one of your legs, through your body, and down the other. And here's a fascinating and tragic fact. This is why animals like cattle are so much more vulnerable. The wider stance between their front and back legs creates a much bigger voltage difference, making them an easier target for that ground current.
Okay, so knowing all this science is fascinating, but staying safe is obviously what really matters. So let's quickly go over some simple safety rules, for both when you're outside and when you're inside.
All right, if you're caught outside, get out of open areas like fields or playgrounds. Stay away from tall, isolated trees. And if you're really caught with no shelter, squat down with your feet as close together as you can. That'll minimize the risk from that step potential we just talked about. Oh, and by the way, a fully enclosed car is actually a very safe place to be. The metal body acts like something called a Faraday cage, so the electricity just flows over the outside of the car and into the ground, keeping you safe inside.
Now for inside, the risks are definitely lower, but they're still real. It's a good idea to unplug your expensive electronics, avoid using corded landline phones. If lightning hits the line, that charge can travel right into your house. And of course, the most important thing is to make sure your home's electrical system has a properly installed earth wire.
And I want to leave you with one final and absolutely critical piece of information. It's a huge myth that someone who's been struck by lightning is still electrified and dangerous to touch. That is completely, 100% false. The electrical charge passes through them in an instant. They are safe to handle, and giving them immediate first aid could absolutely be the difference between life and death. Just knowing that one simple fact could empower you to save someone's life one day. It's something to think about the next time you watch a storm roll in.